Hi friends, I am Minakshi, student of BSc Chemistry Honor second year, 4th semester from Pandit Nekinam Sharma Government College, Rohtak. Today I am going to read the chapter Thermodynamics 3, part 3. So let's start. Work function, Helmholtz free energy and Gibbs function, Gibbs free energy. In addition to the various thermodynamic quantities like internal energy, work, heat, enthalpy, entropy, discussed earlier, two more thermodynamic quantities used very frequently in the study of chemical thermodynamics are work function and Gibbs free energy. They are briefly described below. Work function, Helmholtz function or Helmholtz free energy. It is usually denoted by the symbol A from the German word Arbeit, which means work, and is defined by the equation A is equals to U minus T S, where U is the internal energy of the system and T is the temperature and S is the entropy. Since U, T and S are the function of the state of the system only, therefore A also must be a state function. In order to understand the physical significance of work function, consider an isothermal change taking place at temperature T, then A1 is equals to U1 minus TS1 for initial state, A2 is equals to U2 minus TS2 for final state, where A1, U1 and S1 are respectively the values of the work function, internal energy and the entropy of the system in the initial state, and A2, U2, S2 are the corresponding values in the final state. Increase in a function A accompanying the process will be given by A2 minus A1 is equals to U2 minus TS2 minus U1 minus TS1. So here we go. The final results come out to be delta A is equals to delta U minus T delta S, where delta U is equals to U2 minus U1, the change in the internal energy of the system, and delta S is equals to S2 minus S1 is the change in the entropy of the system. Now, according to the definition of entropy change, we know that delta S is equals to Q reversible upon T. Further, according to the first law of thermodynamics as applied to an isothermal reversible process, we have delta U is equals to Q reversible minus W max. The minus sign before W has been used to indicate that the work has been done by the system during the change under consideration. Putting the values of delta S and delta U from equation 5 and 6 in the equation 4, we get delta A is equals to Q reversible minus W max minus TQ reversible into Q reversible upon T. Here the final result comes out to be minus delta A is equals to W max. Thus, for a process occurring at the constant temperature, the decrease in the work function A is equals to the maximum work done by the system. In fact, it is for this reason that this thermodynamic quantity has been termed as a work function, although at one time it was called the Helmholtz free energy. Gibbs function or Gibbs free energy. This is usually denoted by G and is defined by the equation G is equals to H minus Ts, where H, T and S are the heat content, enthalpy, temperature and the entropy of the system respectively. As before, since H, T and S are the function of the state, therefore G is also function of the state of the system only. Hence, for the isothermal process occurring at temperature T, we can write del G1 is equals to H1 minus TS1 for initial state. For final state, G2 is equals to H2 minus TS2. G2 minus G1 comes out to be H2 minus S1 minus T bracket S2 minus S1. The final results comes here. Delta G is equals to delta H minus T delta S. Delta G is equals to G2 minus G1. Delta H is equals to H2 minus H1, which are the change in the Gibbs free energy of the system and the change in the enthalpy of the system respectively. Delta S is equals to S2 minus S1 is the entropy change of the system. The physical significance of Gibbs free energy may be obtained as follows. At constant temperature T, delta S is equals to Q reversible upon T, T delta S is equals to Q reversible. अब इनको इधर से उधर लेके गए तो ये इक्वेशन हमारी आ गई. At constant pressure P, delta H is equals to delta U plus P delta V. Substituting the value of T delta S and delta H from equation 12 and 13 in equation 11, we get delta G is equals to delta U plus P delta V minus Q reversible. Then rearranging the equation, we get delta U minus Q reversible plus P delta V. This is the equation number 14. Now according to the first law of thermodynamics, delta U is equals to Q reversible minus W max. The minus sign before the W indicates that the work is done by the system, or delta U minus Q reversible is equals to minus W max. Substituting this value in the equation 14, we get delta G is equals to minus W max plus P delta V. Delta G is equals to W max minus P delta V. But P delta V is the work of the expansion done by the system corresponding to the increase in volume delta V. Hence, W max minus P delta V stands for the maximum work other than the work of expansion. This is called the maximum net work available for the process. From the process, hence, we conclude that for a process occurring at the constant temperature and constant pressure, the decrease in the Gibbs free energy is equal to the maximum net work obtained from the process, that is total work minus the pressure, volume work, or the work of expansion. It is because the change in the delta G is measure of the useful work done that the G has been called the free energy. It may be further mentioned here that it is customary to refer to Gibbs free energy simply as a free energy. The designation Gibbs or Helmholtz is added only when necessary for the clarity. Variation of the Helmholtz function, work function with temperature and volume. Variation of Helmholtz function, work function with temperature and volume. The work function is given by the equation A is equals to U minus Ts. The complete differentiation of this equation gives dA is equals to du minus Tds minus Sdt. Equation 2. By definition of the entropy change, we know that the ds is equals to Q reversible upon T. Equation 3. Further, from the first law of thermodynamics, we have Q reversible is equals to du minus del W. Equation number 4. And if the work is restricted to the work of expansion only, then the del W minus del W is equals to P dV. Equation number 5. Putting this equation value in equation 4, we have del Q reversible is equals to du plus P dV. Putting this equation in the equation third, we get ds is equals to du plus P dV upon T. Tds is equals to du plus P dV. Putting this value in equation 2, we obtain dA is equals to du minus P dV minus SDT. du से du cancel हो गया इधर, and finally it comes minus P dV minus SDT. If the temperature is kept constant, dt is equals to 0, then the equation 8 takes the form dA at constant temperature is equals to minus P dV at constant temperature. Then the delta A or del A upon del V at constant T is equals to minus P. If the volume is kept constant, dV is equals to 0, the equation 8 becomes dA at constant V is equals to minus SDT at constant V. Then the equation becomes del A upon del T at constant V is equals to minus S. The change in the work function for a complete process under isothermal condition can be calculated as, for an infinite simal change under isothermal condition, equation 9 may be written as dA at constant T is equals to minus P dV. For a complete process under isothermal condition, when the volume changes from V1 to V2, we will have delta A at constant T is equals to minus integration from V1 to V2 P dV. Putting the value of PV is equals to nRT, that is P is equals to nRT upon V. For n moles of an ideal gas, we get delta A at constant T is equals to minus integration from V1 to V2 nRT upon V dV. Delta A at constant T is equals to minus nRT ln V2 upon V1. Delta A at constant T is equals to minus W maximum. The variation of the Gibbs free energy with temperature and pressure. The free energy is given by the equation G is equals to H minus T delta S, By the definition of enthalpy, H is equals to U plus PV. Putting this value in the equation 1, we get G is equals to U plus PV minus TS. Complete differentiation of this equation gives dg is equals to du plus pdv plus vdp minus tds minus sdt. ds is equals to del q reversible upon t, then it becomes equal to du plus pdp upon t. TDS is equals to du plus PdV, equation number 5. Substituting this value in equation number 4, we obtain dg is equals to du plus PdV plus VdP minus bracket du plus PdV bracket close minus STT. Finally, it comes VdP minus STT, or the dg is equals to VdP minus STT. This is the final equation number 6. This is an important expression which gives the change in the free energy with change in pressure and change in temperature in reversible process. Equation 6 is called the total differential equation. If the temperature is kept constant, dt is equals to 0, then equation 6 becomes del G at constant T is equals to VdP at constant T, or del G upon del P at constant T is equals to V. If the pressure has been kept constant, dP is equals to 0, so del G is, or dg at constant P is equals to minus sdt at constant P. Del G upon del T at constant P is equals to minus S. Equation 8 and 9 given the variation of free energy with pressure and temperature. The change in the free energy for a complete process under the isothermal condition can be calculated as follows. For an infinitesimal change under isothermal condition, the equation 7 may be written as dg at constant T is equals to VdP. For a complete process under isothermal condition, when the pressure changes from P1 to P2, we will have delta G at constant T is equals to the integration from P1 to P2 VdP. Equation number 11 here. Putting PV is equals to nRT, that is V is equals to nRT upon P for n moles of an ideal gas, delta G at constant T is equals to integration of from P1 to P2 nRT upon P dP, that is equals to nRT को हम बाहर ले लेंगे इंटीग्रेशन से P1 to P2 dP upon P, nRT ln P2 upon P1. Further, for an isothermal process, P1 V1 is equals to P2 V2, or P2 upon P1 is equals to V1 upon V2. Substituting this value in the equation number 12, we get delta G at constant T is equals to nRT ln V1 upon V2. This is the same expression as equation number 13, page number 115, for the change in the work function. Thus delta G at constant T is equals to delta A at constant T. This appears to be in contradiction with the result discussed earlier in the section 2.14. However, it may be understood clearly that the equality holds good for an ideal gas but not in general. Criteria for the feasibility or spontaneity of the process. As already discussed in section 2.6 and 2.7, the net entropy change for a combined system and the surrounding delta S of system plus delta S of surrounding can be taken as a criteria for the feasibility or the spontaneity of a process. The results arrived at were: if the delta S of system plus surrounding is greater than 0, then the process is irreversible, that is, it is spontaneous or feasible. If delta S of system plus delta S of surrounding is equals to 0, the process is reversible, that is, system is in equilibrium. The above two results may be combined and put in the form delta S of system plus delta S of surrounding greater than or equals to 0, where the sign greater than refers to irreversible process or the spontaneous process. The sign equal refers to the reversible process or the state of the equilibrium. The above criteria, however, requires knowledge for both delta S of system and surrounding, which is not convenient. Hence, a number of other criteria which require the knowledge of the change in some thermodynamic quantity of a system only are preferred. These may be derived as follows. For an infinitesimally process, the above criteria may be written as delta S of system plus delta of S of ds of system plus ds of surrounding is greater than or equals to 0. The sign greater than stands for irreversible process and the sign equal to stands for reversible process. If the surrounding loses heat del Q reversibly and isothermally at temperature T, then which may be absorbed by the system reversibly or irreversibly, ds of surrounding is equals to minus del q reversible upon t. Further, according to the first law of thermodynamics, del q reversible is equals to du plus pdv. Substituting this value in equation number 3, we get ds of surrounding is equals to minus du plus pdv upon d. Substituting this value in the equation 2, we get ds system is minus du plus pdv upon t is greater than or equals to 0. TDS minus du minus pdv is greater than or equals to 0. TDS greater than or equals to du plus pdv, where ds stands for the entropy change of the system and the subscript system has been omitted. The equation 6 is the basic equation which leads to a number of criteria for prediction of feasibility of a process. In this equation, the sign equals to stand for a reversible process and the sign greater than for the irreversible process. From equation number 6, the various criteria may be deduced as follows. In terms of entropy change of the system, if the internal energy and the volume of system are kept constant, du is equals to 0, dv is equals to 0. Then from the equation 6, we have TDS constant u and constant v is greater than or equals to 0. ds at constant u and v greater than or equals to 0, where the sign equal to is for reversible process and sign greater than for reversible process. The subscript u and v indicate the constancy of these properties. In terms of internal energy change of the system, if the entropy and the volume of system are kept constant, ds is equals to 0, dv is equals to 0, then du at constant v, constant s and v will be smaller or equals to 0, where sign equal to stand for reversible process and sign smaller for the irreversible process. This implies that if a process under constant condition of the entropy and volume is accompanied by decrease of the internal energy, the process is irreversible. If no change of the internal energy takes place, then the process is reversible. Then alternatively, this result may be derived as follows. For a reversible process, delta S is equals to summation del Q upon T or is equals to Q upon T. Since a reversible process is accompanied by the net increases of entropy, for an irreversible process is accompanied by net increase of entropy. For a reversible process, delta S is greater than summation of del Q upon T, or delta S is greater than q upon t. For an infinite simul process, we can write delta S is equals to del q upon t. For reversible process, delta S is greater than del q upon t. For irreversible process, combining the two results, we can say ds is greater than or equals to q upon t, where the sign equals to stand for reversible and sign greater than for a reversible process. Putting del q is equals to du plus p dv from first law of thermodynamics, we get ds is greater than or equals to du plus p dv upon t. Tds is greater than or equals to du plus p dv. In terms of enthalpy change of the system, by definition of the enthalpy H, we know H is equals to U plus PV. Complete differentiation of this equation gives dH is equals to du plus P dV plus V dP. Du plus P dV is equals to dH minus V dP. Putting this value in equation number 6, we get TdS is greater than or equals to dH minus VdP. For entropy and pressure of the system are constant, kept constant, ds is equals to 0, dp is equals to 0, so that 0 is greater than or equals to dh at constant s and p. dh at constant s or p is smaller than or equals to 0. Equals to refers to a reversible and smaller than sign refers for irreversible process. In terms of change in work function of the system, by definition, a work function A is given by A is equals to U minus ds. Differentiating this equation completely, we get dA minus du. dA is equals to du minus tds minus sdt. tds is equals to du minus sdt minus dA. Putting this value in equation number 6 we get du minus sdt minus dA is greater than or equals to du plus pdv. Minus sdt minus dA greater than or equals to pdv. Sdt plus dA is smaller than or equals to minus pdv. If dt is equals to 0, dv is equals to 0, dA at constant t and v is smaller than or equals to 0. Equal sign represent reversible process and smaller than sign represent irreversible process. In terms of free energy change of the system, G is equals to H minus Ts, H is equals to U plus PV, G is equals to U plus PV minus Ts. Complete differentiation of the equation dg is equals to du plus pdv plus vdp minus tds minus sdt. de plus pdv is equals to dg minus vdp plus tds plus sdt. Putting this value in equation number 6, we get TDS is greater than or equals to dg minus vdp plus tds plus sdt. 0 is greater than or equals to dg minus vdp plus sdt. dg minus vdp plus sdt is smaller than or equals to 0. If the pressure and temperature of the system are kept constant, dp 0, dt 0, then dg at constant t and p is smaller than or equals to 0. The criteria in the terms of free energy change is the most significant because most of the processes take at constant temperature and pressure. This criteria implies that delta G at constant P and T is smaller than 0. The process is irreversible, that is, it is feasible. If dg at constant P and T is equals to 0, process is reversible, system is in equilibrium. If dg is equals to Pt, dg at constant P and T is greater than 0, then the process does not occur and it is not feasible. Limitation of the criteria of the spontaneity. No doubt the various criteria discussed above are helpful in predicting the spontaneity of a process, but they do not tell anything about the following: the extent to which reaction takes place, the rate at which the reaction proceeds, and the mechanism by which the reaction proceeds. The advantage of free energy criteria over the entropy change. An important advantage of free energy criteria over the entropy criteria lies in the fact that the former requires free energy change of the system only at constant P and T and is not concerned with what is happening into the surrounding, where the latter or the entropy change criteria requires the total entropy change of the system and the surrounding, that for the process to be spontaneous, delta S total is equals to delta S of system plus delta S of surrounding must increase. Gibbs-Helmholtz equation. Gibbs energy is given by G is equals to H minus Ts. Equation number 1. For an isothermal process, we can write del G1 is equals to H1 minus Ts1, G2 is equals to H2 minus Ts2. Subtracting the equation 2 from equation 3, G2 minus G1 is equals to H2 minus H1 minus T bracket S2 minus S1. Delta G is equals to delta H minus T del S. Taking up equation number 1 again, putting H is equals to U plus PV, we get that G is equals to U plus PV minus Ts. Differentiating this equation completely, dg is equals to du plus pdv plus vdp minus tds minus sdt. ds is equals to q reversible upon t. By differentiating the definition of entropy change, du plus pdv upon t, first law of thermodynamics, q reversible is equals to du plus pdv. tds is equals to du plus pdv. Substituting this value in equation number 6, we get dg is equals to vdp minus sdt. If pressure is kept constant, dg at constant p is equals to minus sdt at constant p. Del g upon del t at constant p is equals to minus s. For initial state, del g 1 upon del t at constant p is equals to minus s1. For final state, del g2 upon del t at constant p is equals to minus s2. Del g2 upon t at constant p minus del g1 upon del t at constant p is equals to minus s2 minus s1 minus s2 plus s1, and finally it comes minus delta s, or it may be written as del g2 minus g1 at upon del t at constant p is equals to minus delta s. Substituting this value of minus delta S in equation number 4, we get delta G is equals to delta H plus T bracket delta G upon delta T at constant P. This is the most common form of the Gibbs-Helmholtz equation. Starting with the expression of work function A is equals to U minus Ts and proceeding exact in the similar manner as above, the following analogous expression can be derived. Delta A is equals to delta U plus T bracket del delta A upon del T at constant V. This is another form of Gibbs-Helmholtz equation. Further, sometimes Gibbs-Helmholtz equation is put still in another form, which is derived from the equation. Dividing equation number 11 through by t square, we get delta G upon T square is equals to delta H upon T square plus 1 by T del delta G upon del T at constant P. And finally, it comes del delta G upon T upon del T at constant P is equals to minus H upon T square. It may be noted that all the forms of Gibbs-Helmholtz equation involve quantity like the delta G, delta H, delta A or delta U, which are state function and do not depend upon the path followed. Hence, the Gibbs-Helmholtz equation is general equation applicable to the reversible as well as irreversible process. Application of the Gibbs-Helmholtz equation. One of the application of the Gibbs-Helmholtz equation is that knowing the free energy change at any two different temperature, the enthalpy change accompanying the process can be calculated. However, the most important application of the Gibbs-Helmholtz equation is in the study of galvanic cells, which is briefly explained below. When redox reaction is allowed to take place in a single beaker, heat is evolved. Earlier, it was believed that when same reaction is allowed to take place in an electrochemical cell, the electrical energy produced was equivalent to the heat evolved. However, later on it was found that the number of cases the electrical energy produced is not equivalent to the heat evolved. This was explained by Gibbs and Helmholtz by stating that the electrical energy produced was equal to the decrease in the free energy minus delta G accompanying the cell reaction. They pointed out that if n is the number of electrons given out by one of the electrodes or taken up by the other electrode, then the quantity of the electricity produced is equals to Nf Faradays, where F is equals to 1 Faraday 96500 Coulomb. If E is equals to E is EMF of the cell, then the electrical energy produced is NFE. Decrease in free energy delta minus delta G is equals to NFE. For substituting this value in Gibbs-Helmholtz equation, we get minus NFE is equals to delta H plus T bracket del minus NFE upon del T at constant P. NFE is equals to minus delta H plus T NF upon del E into del E upon del T at constant P. Thus, knowing the temperature coefficient of the EMF of a cell, delta E upon del T at constant P and delta H can be calculated if E is known or vice versa. Evidently, the electrical energy produced is equals to the heat evolved minus delta H only when del E upon del T at constant P is equals to 0. Nernst heat theorem. W. Nernst made a detailed study about the variation of enthalpy change delta H and free energy change delta G of the system with degrees of the temperature. The result thus obtained are called Nernst heat theorem and are briefly explained below. According to the Gibbs-Helmholtz equation, delta G is equals to delta H plus T bracket del bracket delta G upon del T at constant P. From this equation, it is evident that at absolute zero, that is when temperature is equals to 0, delta G is equals to delta H. However, Nernst observed that as the temperature is lower toward absolute zero, the value of delta G upon del T decreases and then approaches zero asymptotically. This means that the delta G and delta H are not only equal at the absolute zero, but the values approaches each other asymptotically in the vicinity of this temperature. This result is known as Nernst heat theorem. Mathematically, it can be explained. Limit tends to t tends to 0. D delta G upon delta T is equals to limits T tends to 0 d delta H upon dt is equals to 0. In figure, delta G has been shown as greater than delta H at temperature away from the absolute 0. However, the reverse is also possible because delta G upon del T can both positive or negative, but we know that delta G upon del T at constant P is equals to minus delta S, and delta H upon delta T at constant P is equals to delta Cp. By combining these results, we get equation limits t tends to 0 delta S equals to 0 and limits t tends to 0 delta Cp is equals to 0. Since gases does not exist at the absolute 0, this means that the Nernst heat theorem is not applicable to the gases. Similarly, it has been found to inapplicable to the liquids also. Thus, Nernst heat theorem is applicable to solids only. Third law of thermodynamics. The result of the Nernst heat theorem led to an inset is generalization, which has been called as the third law of thermodynamics. In other words, third law of thermodynamics follows from the result of Nernst heat theorem as briefly explained below. According to the Nernst heat theorem, delta Cp approaches 0 at 0 Kelvin. This implies that at 0 Kelvin the heat capacity of the reactant and the product become equals. It seems most probable that at 0 Kelvin all substances have the same heat capacity. On applying quantum theory to the heat capacities of the solid, it is found that heat capacity of solid tend towards 0 at 0 Kelvin. Thus, Nernst heat theorem leads to the following result: limits T tends to 0, Cp is equals to 0. Also from Nernst theorem, limits T tends to 0, delta S is equals to 0. Predicting exactly in the same way as above, it may concluded that all the solids have the same entropy at above absolute 0 of the temperature, and it tends towards 0 at absolute 0 of the temperature. Limit T tends to 0, S is equals to 0. This generalization is known as third law of thermodynamics. The entropy of all perfectly crystalline solid may be taken as 0 at absolute 0 temperature. In broader sense, this law is usually stated as follows: every substance has a finite positive entropy, but at the absolute 0 of temperature, the entropy may become 0. In fact, it does not become 0 in case of perfectly crystalline solids. Like the first and second law, this law is also a generalization based upon the experience and is no direct proof of this law. However, the law has been verified in a number of ways and there is no doubt about the validity of the law. It is important to note that the third law of thermodynamics does not state the entropy are 0 at temperature is equals to 0. It merely states that all the perfectly crystalline solid have the same entropy at temperature T is equals to 0. Choosing a common value as 0 is the only matter of convenience. Importance of the third law of thermodynamics. The importance of the third law lies in the fact that it helps in the calculation of the absolute entropy of the elements or the chemical compounds at any desired temperature. The infinitesimal entropy change is given by ds is equals to del q upon t. Cp is equals to del q upon dt, so that del q is equals to Cp dt. Substituting the value of equation number 1, we have ds is equals to Cp dt upon t. Hence, the entropy change of the substance when its temperature changes from absolute 0 to the temperature T will be obtained from the equation integration S is equals to S naught, S is equals to S. Integration from S naught to S, ds is equals to integration T naught to T Cp dt upon T, or St minus S naught is equals to integration 0 to T Cp dt upon T, where S naught is the entropy of the substance at absolute 0 and St is the entropy of the substance at temperature T. Now, according to the third law of thermodynamics, S naught is equals to 0, St is equals to integration 0 to T Cp dt upon T is equals to integration from 0 to T Cp dt Cp d ln T. Thus, the entropy S of the substance at temperature T can be calculated from the measurements of the heat capacity at the number of temperature between 0 Kelvin to 7 degree 0 degree Kelvin to 7 degree Kelvin. The integral is in the equation 3 can be evaluated by plotting Cp versus ln T, that is 2.303 log T, or Cp upon T versus T. Then measuring the area under the curve between T is equals to 0 to T. Thus, the evaluation of entropy requires the measurement of heat capacity at different temperatures. However, a problem arises with the measurement of heat capacity at low temperature. For example, at a plot given in 3.2 above, the heat capacity along the curve BC are the experimental values, the point B corresponding to the lowest temperature up to which the experimental values can be determined accurately. To get the complete area under the curve from T to 0 Kelvin, the extrapolation of the graph of the curve is done as shown in the figure BA of the curve. The value corresponding to the extrapolated portion is usually found by applying d by third power law of the heat capacity of the solids at low temperature. Cp is equals to AT cube, where A is the empirical constant. If it corresponds to the temperature T1, C corresponds to the temperature T, and remembering that A corresponds to 0 Kelvin, integral given in equation number 3 can be split into two parts. St is equals to integration 0 to T1 Cp upon T dt plus integration from T1 to T Cp upon T dt. The value of the first integral can be found by substituting the value of Cp from equation number 4. We get 0 to T1 Cp upon T dt is equals to 0 to T1 At cube is equals to At cube upon T dt is equals to 0 to T1 At square dt is equals to At1 cube upon 3. Equation number 5 become St is equals to At1 का cube upon 3 plus integration from T1 to T Cp upon T dt. Cp is equals to At cube, therefore At1 cube upon 3 is equals to 1 by 3 Cp at T1. This means that the entropy change from 0 Kelvin to T1 is equals to 1/3 of the value of Cp at T1 and can be simplified further to form St is equals to 1 upon 3 Cp at T1 plus T1 to T Cp upon T dt. It is important to remember the calculation as described above are applicable only to solid involving no polymorphic change between 0 degree to 7 degree Kelvin. If some polymorphic change is involved in this range, the entropy of the transition delta H upon T, where delta H is the molar heat of the transition and delta T is equals to the transition temperature, will have to be included in the value calculated above. For liquid and gaseous substances, the total absolute entropy of the substance at given temperature will be the sum of the entropy changes which the substance has to undergo in order to reach the particular state, starting from the crystalline solid to at absolute zero. Thus, if a substance is gaseous at temperature at 1 atmosphere pressure and 29 degrees Celsius, the entropy of the gas at 25 degrees Celsius will be the sum of the following entropies. The entropy of the heating of the crystalline solid from T is equals to 0 to Tf, the melting or the fusion temperature. The entropy of fusion delta FHTF, where delta FH is latent heat of melting or fusion. The entropy of heating of liquid from Tf to Tb, the boiling point. The entropy of vaporization delta V. Delta VH is the latent heat of vaporization. The entropy of heating of gas from Tb to 25 degrees Celsius. Thus, the complete expression of the calculation of the entropy at temperature T may be written as St is equals to integration from 0 to Tf Cp S dt d ln T plus delta heat of fusion upon Tf plus integration from Tf to Tb Cp L d ln T plus delta H of vaporization upon TB plus integration from TB to T, CpG gaseous D, L and T. If the substance is solid at temperature T, only first term is to be taken with Tf is equals to T. If the substance is liquid at room temperature, the first three terms are to taken with Tb is equals to T. If the substance is gaseous, the full equation is to be used. Test of the third law of thermodynamics. By calculating the equilibrium constant K is related to the standard free energy change delta G naught according to the equation minus delta G naught is equals to RT ln K. The standard free energy change is related to the standard enthalpy change delta H naught and standard entropy delta S naught according to the equation delta G naught is equals to delta H naught minus T delta S naught. Putting the experimental value of delta H naught and calculated value of the delta S naught using the absolute value of the entropy obtained from the third law of thermodynamics and applying the relation delta S naught is equals to summation of delta S naught products minus delta S naught of reactants. Delta G naught can be calculated for the reaction putting this value of delta G naught in equation number V1. The equilibrium constant K can be calculated. It is found that for number of reaction the value of equilibrium constant as calculated above comes out to be in close agreement with the experimental value. By comparing with entropy calculated from the statistical mechanics, the absolute entropy calculated on the basis of third law are found to be in complete agreement with those calculated using statistical mechanics. By proving the different allotropic forms of the substance have equal entropy at the absolute zero, the orthorhombic sulfur as alpha changes into monoclinic sulfur beta at the transition temperature 369 Kelvin. The enthalpy of transition is found to be minus 402 joule per mole. Hence, the molar entropy of transition will be given by delta S of transition is equals to the S alpha minus S beta is equals to delta H of transition upon T of temperature of transition. The individual entropy of the two forms can be calculated by measuring their heat capacity from temperature is equals to 0 to temperature is equals to 369 Kelvin. It is found that S alpha is equals to S naught beta plus 337 joule per Kelvin per mole. S beta is equals to S naught beta plus 38 joule per Kelvin per mole. Hence, the transition temperature comes out to be delta S transition is equals to S0 alpha minus S0 beta minus 1 kilojoule per mole. The comparing the equation, finally S0 alpha minus S0 beta is equals to 0. The elements are perfectly crystalline from crystalline form are arbitrarily ascribed a value of 0 for the entropy at absolute 0. Residual entropy. As explained above, the entropies can be determined by applying third law of thermodynamics. These can also be calculated from the statistical mechanism or from the spectroscopic data. It is found that in most of the cases, the agreement between the third law entropies and those calculated from statistical mechanics is very fair. However, in some cases, the experimental values are found from third law is found to be less than calculated value. For example, standard entropies found from the third law are calculated and calculated from statistical mechanics for CO and N2O molecules are given. The lowest value of third law of entropy are explained on the basis of temperature T is equals to 0 Kelvin. The crystal of these substances are not perfect. There is some disorder present in the solid even at temperature T is equals to 0 Kelvin. The entropy which the crystal of a substance has at temperature 0 Kelvin is called the residual entropy. Origin of residual entropy. To understand the origin of residual entropy, let us consider a crystal made up of AB molecule where A and B are similar atoms so that the molecules has a very small electric dipole moment. These molecules can adopt different orientations such as AB, 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 or AB, BA, BA, AB. These arrangements or many other random arrangements that the molecules can adopt have very little difference of energy. Thus, there is a residual disorder, and hence there is a residual entropy at 0 Kelvin. The calculation of residual entropy is done by the formula S is equals to K L N W, where W represents the number of possible orientation of the molecule that are equal probable, that is have nearly the same energy, and hence W is the thermodynamic probability and K is the Boltzmann constant. A few examples of the residual entropy are given below. Residual entropy of CO. Suppose a sample consisting of n molecules of CO. Now, as each molecule can have two orientations that are equally probable, CO, CO, OC, CO, OC, OC, therefore, same energy can be achieved in two n different ways, where W is equals to 2 n. S is equals to K ln 2 n is equals to K n ln 2. For 1 mole of the sample, if 1 mole of the sample is taken, Kn is equals to R, S is equals to R ln 2. By calculating the logarithm, the final answer comes here to be 5.85 joule per Kelvin per mole. The residual entropy of FClO3. FClO3 molecule can have 4 possible orientations with nearly same energy, hence the residual entropy is S is equals to R ln 4. After calculating the logarithm, final answer comes here to be 11.5 joule per Kelvin per mole. In general, if a molecule can adopt p possible orientation at temperature T, then which have nearly same energy, the residual molar entropy will be SR is equals to R ln P. Thank you.